So looking at page 72 in the Unit 3 packet, we're looking at specifically the inference for two-way tables, chi-square. Right, so the assumption is simple random sample, skewed distribution. You're testing for homogeneity, independence, or goodness of fit. You can compare, as an advantage, more than two populations, and it's always right-tailed using only positive values of characteristics of a chi-square test. The added bonus for something like this is now we can look at a two-way table in that we're comparing two variables to each other, two possibly independent variables. So our null and alternative hypotheses boil down to one of these four possible scenarios: independent versus dependence, good fit, not a good fit, all the population proportions are equal or one's different, where there's no association between whatever the row and column variables are versus there's some association. All right. So we determine the critical values using the chi-square table or the Desmos calculator, which we'll get to in a minute. Degrees of freedom is the number of rows minus 1 times the number of columns minus 1. All right, so you're looking at really each row categorized much the same way a goodness of fit test would do it. You know, the k-1 from the first chi-square test that we did, except we have two variables. So the two variables multiplied, or at least the two degrees of freedom multiplied, will give you the degrees of freedom for the two-way situation. And then you compute the value of the test statistic. You can do a lot of it on the graphing calculator, but you still need this information, these formulas. The expected count, and I'll just do a quick snip here. The expected count is row total times column total divided by n, which is also known as the grand total. And then your chi-square value is the same as it was previously. Right? Once you have those values, it's easy enough to do the remainder of the work. All right? And then we could use our calculators to determine test statistics, and if we want to, p-values, and then go from there. All right, so I have an example here. Like I said, I'll just kind of pop in the rules here. I'll just kind of jot it right there. All right, so at the 5% level, test the claim that there's no association between the row variable pass-fail and the column variable math2a / math2. All right, so that's my null. No association. And let me go with a thinner marker. No association between pass-fail and the column variable math2a2. Well, actually, when you think about it, that's what the row and column variables can categorize as, but it's really math and result. I mean, if we're looking for a nice succinct way of saying it, that's probably the best way to do it. The alternative to that would be that there's some association. All right, so some association between those two variables. All right, so we're doing this at the 5% level. All right, so that's my alpha. We need degrees of freedom. All right, degrees of freedom, again, is the number of rows minus 1 times the number of columns minus 1. All right, so when we talk about rows and columns, we're talking about the heart of the table, so we're excluding any totals. All right, so just this part of the table here is what we're looking at. All right, that's 2 by 2. We have 2 rows, 2 columns, so 2 minus 1 times 2 minus 1. 1 times 1 is equal to 1. All right, so I'll go to my chi-square calculator, chi-square distribution. Degrees of freedom, 1. All right, the alpha value. All right, so we need to get our alpha value to be as close to 0.05 as possible based off of this. So I'm going to scroll. Looks like I gotta go left significantly. We want to get as close as possible, even if it means we overshoot it. So this is 0.05125. I just had it. we're at 5. That looks like the, nope, I don't know where it was. It just kind of ran away. 3.8 is what I'm trying to lock it in on. If I can't, then I will just type it in. Okay, so 3.8. That seems to be the winner. That's the closest one to 0.05. All right, so in the right tail, I have a critical value for chi-square of about 3.8. I mean, according to Desmos, it's exactly 3.8. But that, I say it's about because this area isn't exactly 0.05 in Desmos. So whatever we get as a chi-square is only going to be an approximate, and that's okay. And by the way, the distribution is chi-square. All right, it's a nice, almost script looking at with a nice straight through. That's our chi-square distribution. All right, if you want to write it out in words, that's fine too. All right. In order to come up with our statistics, I'm sorry, not statistics, the test statistic, we need some background information. Now, statistics, normally we would list out like a mean, a standard deviation, things like that. We don't really have that for something like this. All the work that we do for statistics is going to happen really in the table until we get to this part. All right, so we need expected counts first, which is the row total times the column total divided by the grand total. All right, so we're just going to crunch those numbers off on the side here. So we'll go case by case. It's only 2 by 2, so there's 4 computations. So let's say we're focusing on the number 7. That corresponds with a row total of 26, a column total of 16. So we do 16, or 26 we can do first, doesn't matter, it's commutative, times 16 over the grand total, which is 38. All right, so we should have, and we go 3 significant here, 10.947. All right, so the number they gave us is the observed. All right, so this is the observed. The number that we came up with is the expected. All right. So we do the same thing again, this time for the number 19, which has a row total of 26, a column total of 22. Grand total is always going to be the same. This one should be 15.0526. All right. So then the number 9 is next on the list. That's got a row total of 12, column total of 16. So 12 times 16 over the grand total, which is 5.0526. And then the last one, fresh new color for that. Row total times column total, so 12 times 22, divided by the grand total of 38 is 6.947. All right, so the printed values, the 7, the 19, the 9, and the 3, those are what values we actually got. You know, look, we conducted a study, and these are the outcomes. What I wrote down in marker, the 10.947 and the 15.0526 and all that, that's what we should have gotten. All right, so what we do is we make a column that consists of all the observed values in a table. We call that first column O and the second one E, just like we did for the homogeneity test and goodness of fit, the last one. All right, so 7, 9, 9, 3. Doesn't matter what order you do it in as long as you get them all in there and their corresponding expected values. 10.947, 15.0526, 5.0526 and 6.947. All right, those are the four entries that we're going to use in our chi-square formula. Chi-square is equal to the sum of O minus E squared divided by E. Observed minus expected squared divided by E. So this is, apologies, this is under test statistic. All right, this is kind of like a, this is my templated response thing. This is actually not really, oh, that works. That's all in the table. All right, so I'm going to use the total function under distribution, not distribution, stats, total, fraction, open parens, O minus E, close it up, square it, divided by E. And that'll give me my test statistic. All right, so my chi-square is going to be about 7.785. All right, so we got 0 over here, we got the degrees of freedom in here. 3.8 is the cutoff between the non-rejection region and the rejection region. We know that this goes out to infinity. So we know our test statistic is probably going to be in here somewhere. It's definitely going to be in the shaded region. It's just a question of how far in. All right. We're not going to worry about the p-value when it comes to a chi-square test because we're using the Desmos calculator. So what we're going to do is just work off of this and say, well, it falls in a rejection region, so that's telling us to reject the null hypothesis and go with the alternative. So there is sufficient evidence to reject the claim that there is no association between math. We don't really have context here, so math what, and result pass fail. Maybe we're talking about a course, math course. That there is no association between math, but they only wrote math, so we don't even know. Math type. We can make the assumption that it's course. Course. And result at the 0.05 significance level. Now that just happened to be what they were asking about. They didn't ask us whether or not anything else was true. So we're done with our conclusion at this point. So this is gone, as is this.